Morning, Gabriel.
Morning.
How was your weekend?
It's good.
Nice. That's good to hear.
Yeah.
You guys have a lot of snow in Pocatello today?
Yeah.
Yeah, same here. Probably 2 or 3 inches up here.
Yeah. Similar to last year.
Good morning, Daniel.
Morning.
How are you doing today?
Doing all right. It's cold, but it's all right.
Yeah, it's cold here. I think there's probably 2 or 3 inches of snow here too.
Yeah, it's the same. Yeah.
Yeah. So yeah, you never know here. It's already winter time.
Mm-hmm.
Great. Morning, Cade, Mario. How are you all doing today?
Good morning. I'm doing good. How are you?
Not too bad. Yeah, just talking about the snow. It's everywhere.
Oh, yeah.
Yeah, it's really wet and heavy too. Our branches were all we have some bushes, and they were like all drooped down almost to the ground.
Mm. It's getting cold now.
Yeah. Yeah, it's a little I love skiing. And I like backcountry skiing, but usually you don't want it to snow quite this early for it because if it snows too early, like if it gets warm later in October, the snow will melt a little bit, but not all the way. And like all those like snowflakes and that crystals, they kind of like degenerate into um, like almost more like grains of sugar, where like they lose all the branches to the snowflake structure, and then when it does that, it they don't bond together very well, so it makes a lot worse avalanche conditions. So
Uh-huh.
it's a little too early to be really excited for me, but it's still fun.
Right. Well, hopefully we get snow,
Yeah.
unlike last year. It's just cold and dry.
Yeah, that's weird. In Pocatello, it was just cold and dry last year, mostly.
Yeah.
Interesting. It wasn't, yeah, here in Idaho Falls in town, we didn't get a ton, but like in the Teton area, which is where I usually go, it got like February was the third snowiest month that they had recorded. It snowed a lot every week up there.
Interesting.
Yeah, it's crazy how like localized weather can be, just without moving too far, how much different weather you can get.
Yeah.
All right, well, it's a couple minutes after 8 now, so let's see, a few announcements. The first one is, I think, well, you guys are all here, so I kept making a mistake on the quiz 5, but I finally changed the due date and the restrictions correctly, so it shows up as being on Thursday. So hopefully you all noticed that, and you are all here, so you all noticed that. But again, the quiz 5 and the homework 5 is due on Thursday. You probably also saw the announcement. I did make one video that I posted onto YouTube about problem 510 in the homework, which was the third problem. So hopefully that gives you one more chance to see a solution method for this homework, since we didn't have class last Thursday. So there's only 4 problems, and I think that makes it so that we've looked at half of them together. The second problem is quite similar to the first problem. It just has integration limits. And the fourth problem is very similar to the third problem. So does anyone have any questions about the homework? The homework, the 5 that's due on Thursday? Okay. How are you all finished with it? Or how about, is anyone finished with it?
I am not finished.
I'm not
with
yet.
it.
Okay, which problems do you still have left? I think I heard a few of you not quite finished. Daniel, Cade, do you know which problems you have left to do?
Just the last problem.
Okay, all right. Do you feel pretty confident about how to do it?
Yeah, I think so. You just have to set up the integral.
Yep. Yeah, you just
do
need to set
that.
up the integral. Yeah. Daniel, do you feel confident?
Yeah, on the last one, yeah.
Okay. All right,
Okay.
that's good. And then, yeah, you do. Gabriel, you're also good. Mario, you good?
Yeah. There's
Okay.
also talks about the third quiz.
Yeah.
Okay. All right. So yeah, hopefully that helps. If you do run into any questions, of course, send me an email. But I think especially so the BO the method, right? The method for setting up the integrals using the BO cookbook, it's almost the same as the Coulomb's law. We just do the cross product instead of the dot product, which of course, I think the cross product is a little trickier to do correctly, but as far as all the other steps, right, it's almost the same. So so I think you guys are all quite good at doing completing those steps, determining that vector from the origin to the point of interest. So that's great. Okay, so if you do have any questions, let me know. We will today start in on homework 6 then. So homework 6, we're going to see another set of problems that are similar to what we've done before. Okay. So in homework 6, we'll look at Ampere's law, and we can consider Ampere's law as the same, kind of almost the same situation as we did with Gauss's law. So when you have any general problem, and then you could also have symmetrical problems. So for the general case, right, if we were dealing with the electric field, for the electric field, we follow Coulomb. And then for the general case, for the magnetic field, we use Biot-Savart. And then for the symmetric case, right, we can apply the Gauss's law, right? So these were all the things like in the exam, that's the sphere, concentric spheres, concentric tubes. So when you have special symmetric cases, there are often some shortcuts you can take in order to solve these problems more quickly. So when we're dealing with the electric fields, you would use the Gauss's law. And for magnetic fields, we'll use Ampere's law. So this is going to be another special case where we can look at symmetry and use the symmetry to solve for special cases. So that is what the first half of this homework is going to be. So I think homework 6 has kind of 2 parts. So part 1 is applying Ampere's law. And part 2 is magnetic boundary conditions. So, and these are all under the category of magnetostatics. So hopefully what you're all seeing, right, is that when we look at the magnetic field, we're looking for H, it turns out that, right, almost everything that we do is going to be very similar to something that we already saw in the electrostatics. That's in some cases it's slightly different because we may have to do the cross product, or the field direction, right, is different, but the solution methods often show a lot of similarities. So that's what we're going to be looking at for homework 6. And we'll look at homework 6 problems. We'll look at them today, Thursday, and then the homework 6 will be due next Tuesday. One other piece of information that I wanted to share with you before we get started is on the main page of the Moodle page. I added this section, this mid-semester feedback. So if you have any comments or things that you would think could make the class better, please do let me know. So I have it set to, you can see, I'm not sure if this will tell you or not, but right, I have this set to anonymous, so I can't see who submits this. So you're welcome to write whatever you want to say, and I won't be able to tell who wrote it. But basically it's just 2 questions. What do you like about the class? What do you think could be different to make it better? So I can't guarantee that I'll implement any of them, but I will, if you have something that you would like to say, put it in there and I will try. So in the past I've made changes to the course based on the answers that I got, especially if, you know, multiple people ended up writing something similar. So please take a look at this. And if you have anything that you think might make the class better, I would love to hear it. So I'm always looking for ways to improve the class. So that is the last announcement that I wanted to make. Does anyone have any just general comments right now that they have that you think could make the class better? Or or anything that you do like about the course so far?
I like that we are able to work on the homeworks together. That helps a lot.
Yeah, that's good. I'm glad that helps. Sometimes I, intentionally make, some problems that are a little difficult so that I can help you or help guide it. So I'm glad that's working for you, Cade. Anyone else? All right. Well, thank you for sharing that, Cade. And again, anyone else who has any thoughts, feel free to go and write them. Because it's anonymous, right? I can't give, I'd love to give extra credit, but I can't actually, since I don't know who did it, I can't actually give any incentive. So, because I won't know who submitted it. So really it'll just be to improve the course, which I think is worth it in and of itself. So take a look at that later. And yeah, let's get started on this homework. So this is the problem 1. So it says we have an infinitely long cylindrical structure, right? So we have a cylindrical structure and it's infinitely long. So obviously what we see here, right, we have this cylinder here and we have to assume, right, that it actually does extend in both directions infinitely. Okay. So in this one, right, the z-axis is out of the paper. And as we go on, I think, do you all remember, did you use this notation in your physics class where this is out? And this is in?
Yeah.
Okay.
Yes.
All right. So if you are not familiar with this, just recall, right, these are ways that are often used in vector, anytime you're dealing with like complex 3-dimensional vector structures. If needed, if you have a dimension that's in or out of the page, you'll write that out of the page like this and in like this. And the idea, at least as far as I understand it, is supposed to be like an arrow, right? And so from the top of an arrow, if you're looking at an arrow and the arrow is pointing at you, it might apparently look like this. And if you're looking at an arrow that's pointed into the page, right, you might see this part, and so it might look like an X. Okay, so that's where this notation comes from. And right on here, you can see that this is indeed coming out of the page. This z-axis is pointed out of the page at us. So the z-axis is out of the paper. The shaded regions are made of a semiconducting material with free space between the between and outside. Right, so this is free space here. And out here, this is also free space. And in here, right, this is semiconductor. Does anyone remember? Can you tell me what free space is? What we should remember about free space? All right, let's see here. How about Daniel? What should we know about free space?
Depends on the medium. but I think since the one we use commonly is equals to 1.
Yeah, it's right.
Yes.
Okay. And we can also remember, and this is, I think, the first time we're going to look at this, but the mu r is also equal to 1 in free space. And so we can write our epsilon as epsilon r, epsilon naught, and our mu as mu r, mu naught. Okay. So the relative permittivity and permeability are equal to 1 in free space. All right, there's no metal structures in this, and the outer shell is not grounded. Okay. So we need to find the current density for each region based on what we know. All right, so first of all, just based on what you remember, if you wanted to guess like the general direction of the magnetic field in this, how would you guess the direction of the magnetic field? Do you remember anything with the right hand rule that you can use?
Is it the thumb points in the direction of the current, and then the fingers show the direction of the field?
Yeah, so I can't actually see any of you right now, but try putting your thumb up, okay? Put your thumb up right now in front of you. And your thumb, the direction of your thumb, you should point that in the direction of the current. So whatever direction the current is in, your thumb should also be in. And then the fingers, your fingers are going to curl, right? And the direction that your fingers go is going to be the direction of the magnetic field. Okay. So if your thumb, based on this situation, right, we have a cylindrical structure. So we probably want to consider ourselves in cylindrical coordinates. So what direction are our fingers pointed in? We have our thumb and Z. So what does that make the fingers in? What direction are your fingers pointing?
Would it be phi?
Yeah, the fingers are pointed in the phi direction. So that's that radial direction that wraps all the way around. So we know, we can already guess from this, right, based on this cylindrical structure, right, that we would have, right, an H field, and it could be an R phi or Z. And what we've already determined, right, just by looking at this, is that for this cylindrical case, where it's infinitely long, right, we should expect the magnetic field to be in the phi direction. So what else do you notice about this problem? Is there anything else we should notice? What about, so we're supposed to find it for all of these regions. So region 1, right, is here with the semiconductor, and we have the current. And then in region 2, there's nothing. In region 3, we have more semiconductor. So we know that there is going to be some H1, right? And this one will make, I guess, H3. So what do you think? Do you think H1, how do you think H1 and H3 will interact? Is there a structure or way of combining these that you think it will follow? So I guess if you think yes, they combine somehow, give me a thumbs up. If you think no, they don't combine, give me a thumbs down. All right, so we have one not combining. Let's see, Gabriel, what do you think? Combine or not combine?
Not combined.
Okay, so we got another combine. So Cade, not combine. Mario, what do you think? Do you think they'll combine or they won't combine?
I think they might combine.
Yeah. Is there a reason that you have in your mind of why they might combine?
They're both like, they're not in free space. So they're both in that semi-conducting material.
Yeah, both
That's-
vector fields are in the semiconducting material. What about before, when we looked at electric fields, did those ones combine? They did combine. Do you remember what we called it when we combined them together? We had a special name for it.
Is that superposition or not?
Yeah. So the electric fields did combine with superposition. And what we should prepare for in this case is also that we should be thinking about the fact that we may have a superposition here as well, since we're going to have multiple fields. Okay. So let's keep that in the back of our mind before we go any further. All right. So to recap, we have this solution case. We already determined that if we, for this problem, the magnetic field, we're going to look at cylindrical coordinates. And we've already determined that we think our field should be pointed in this h phi direction. So we've already determined that we should expect our final result to take this form. Okay. We've noticed that we're going to have multiple h fields we can solve for. So both region 1 and region 3 have current, so we expect them to have an associated h field. We know that we're in free space. So now I think that's basically enough to get started. So we have another integral, this Ampere's law, okay? And Ampere's law tells us is written like this. Okay, so can anyone tell me, like, qualitatively, what do you think this integral means? Can you describe like the meaning of what happens with this integral? So let's look at the right side. What does that mean? Don't know. Let's start then with this. What is h dot dl? What does that tell us?
The magnetic field dotted with the change in of
It length.
Yeah, the change in direction, maybe. So if we have a DL, so if we have a closed loop, right, the DL would go all along here, right? So every little bit on here would be a little bit of DL. So let's break this down and say this is a little piece of DL. Okay. And then we also have some current. And we've said that the current rate is going in this positive z direction. So the H, and we determined H already, right, is in the phi. So at one point, let's say that this is H, okay? So what we're doing, right, this is saying for this point on this contour, let's add up the little bit of H that's in the DL direction. And then when we go here, let's do the same thing, right? Let's look at this little DL. And there's some more H in this direction. So let's add that up. And let's keep going down here, right? We have more H and more DL. And let's add it up all the way around. Okay, let's look at this magnetic field. Let's go all the way around this contour and let's add up these little bits of H as we go all the way around, right? That's what this integral is saying. Let's go all the way around and let's go so far that wherever we start, let's keep going, adding up the H in this DL direction. Let's keep going until we reach the end again. And that's this closed loop. And when we do that, what we arrive at, we get this total amount of current. So there's some current in here that's flowing in the positive z direction. And if we keep adding up these little bits of H field all the way around the contour, we will get to an answer that says how much current there was in there. So we have a relationship. It's very similar to our Gauss's law relationship that says that we do a closed contour integral, we will get some relationship. In Gauss's law, the relationship was between the total amount of charge and the electric field. And Ampere's law tells us the relationship is between the total amount of current and the magnetic field. Okay. So let's call this the left-hand side of the equation. And let's call this the right-hand side of the equation. And we already know, what do we already know about this H?
It's going to be in the phi direction.
Yeah, we know that this H is going to be in the phi direction only. Okay, so for the right-hand side, this integral, let's just look at the right-hand side only. And we know that the H is going to be in the phi direction. Okay. Right, so this is the H field here that we just substituted in. All right, so how about the DL? What should DL be? So how about pull out your cookbook if you don't have it handy already and see if you can determine what DL should be. When you've got an answer, shout it out.
Is it RD phi?
Yes, yes. So how did you get to that? And there's one more part. So RD phi, right? And then this is a vector, right? The DL should be a vector. So what should the vector direction be?
The Z, or
So this little DL, it goes all the way around in this direction.
Yeah.
So it's not Z.
Phi.
Yeah, it's phi. And let me give you two ideas about how you can know it's phi. Idea one, and this one isn't foolproof, but we all have already guessed, right? We're pretty clever, right? We've already got to the point of saying, well, this is all symmetrical. We can use Ampere's law. And that's pretty clever of us. And so based on that cleverness, we can already guess that the phi here dotted with the phi here should give us an answer, right? Because if it was in R or Z, right, we would get phi dot with R or phi dot with Z. Those would don't give any, they get equal 0, right? So based on our cleverness, we can already guess, well, phi is a good guess. The second way, right, is that if we look at the contour we made, right, that if the contour went in this direction everywhere, right, this is the R direction. We can see it doesn't go in that, it like loops around. And then also it's clearly not in the Z direction. So based on that, right, we can determine that the DL should be in the phi direction. All right, and we can also look at this, right, see d phi, right, when we move around on this contour, R is constant, right? This is a constant radius. It's not the perfect drawing, right? But R is the same everywhere on here. So when we move around here, R is not changing. We are also looking at this, right? It's flat. Z is not changing. So it's not dr, it's not dz, so it must be d phi. And if you were to go right to the cookbook, right, and in the cookbook, you can see, right, that the DL, right, this is the DL, the total DL option, right, for cylindrical. And we said, okay, it's not in R, it's not in Z, so therefore it must be in phi. And when you're in cylindrical, you need to add on this little R d phi. Okay, so we have something set up for this right-hand side. So on your paper, see if you can solve this integral. See if you can solve this integral, right? This closed contour integral. All right, anyone have an answer? All right, how about at least someone tell me what should the limits be on this for a closed path?
0 to 2 pi.
Yep. All right, so then what should the result of this be?
Two pi r.
Yeah, 2 pi r, and then anything else?
H phi.
Yep, exactly. Okay. So now we have an expression. We've solved, right, this. And arrived here. So we only have to solve this right-hand side once. Okay. Now for each other region, we're going to need to solve for the left-hand side. So the right-hand side, just solve this once. But this left-hand side, we will solve it many different times. Okay, we'll solve it for each time that we have a region. Okay. Okay, so we have 4 regions, so we're going to need to solve the left-hand side for each one of those regions. And the solution for region 1 and region 2, right, they will have some similarities, right? And region 3 and region 4 will also probably have some similarities, right? And these are going to be based on the integration limits. All right, so let's jump in and see what we mean by that. Okay. So this is region, what did I call it? Region 1. Part A, region 1. So somehow now, right, we should solve for the total amount of current in that region. Okay, so if we have, this is that semiconductor right here, and it goes out to as a radius of A. Okay. Let's see here. Has a radius of A, and there's a current that's moving through it. That current amount is this. All right, what kind of integral could we do to find the total amount of current in there?
Surface.
Surface? Is that what I heard?
Yeah.
All right, yeah, so we could do a surface integral, right? And how would we set up a surface integral? Usually has a ds, right? So we should find some integral j dot with ds, and this will give us the total magnitude of the current in there, right? So take all of the j that's going through the surface, right? So this is the surface. Find all of the j, all of the current on the surface, add it all up, and right, that's going to give us the magnitude of the current that's in this. All right, so we already know j, right? J is z hat r cubed. So what should our ds be? So if I move around on this surface, right, we have x, y, and z. When I'm moving around on this surface, what changes? We have r, phi, and z to choose from. What changes on the surface?
E.
Which one?
The phi.
Yep, phi changes. what about R? Does it change? So if I go from here all the way out to here, did I change R? Will I move?
Yes.
Yeah, right. So if I go from the center all the way out to the edge, R does change. But, right, we have X and Y here. So this is on a slice where Z does not change. So Z doesn't change. So we should have a dr and a d phi. So pull up your vector cookbook and see what should the ds be? What should we have any other, besides the having dr and d phi, is there any other variables that should appear in our ds?
Z hat and R.
Yeah, Z hat and R. So on the cookbook, right, this is the choices of ds that we have in cylindrical coordinates. We already determined that it should be dr d phi. So that means this one is out, right, because Z changes. This one is out because Z changes. So we need to use this one. We know that it's vector valued, right? So this one is a vector. So we should have the Z hat included. And then because we're in cylindrical coordinates, right, there should be R dr d phi. All right. What about the limits? Let's talk limits. What should the limits be? What should the limit for R be when we're adding up all the current in here?
Zero to A.
Yeah.
So it should definitely start at 0. And we want to know anything when R is less than A. So what should the upper integration limit be here? Should we go all the way to A, or should we choose
R.
something else? Yes, that's correct. We should only go to R, right? Because in region 1, right, we may have a case, right, where we want to find the field right here. Hopefully you can see that. Let's say R, where R is, it's somewhere less than A at some point right in here. So if we wanted to find the field at this green point, we haven't gone all the way to A. Therefore, we should not add up all of the current, right? Because there is going to be some current that is outside of that green point that's at a radius larger than the point where that green is. So let's just only go up to R and leave this in variable form. For those of you who did say A, keep that in mind, right? Because coming up, right, when we get to region 2, right, we will keep in mind that we probably do want to integrate to A. So just keep that in the back of your mind for now. What about for phi? What should our phi limits be on this?
0 to 2 pi.
Yes, exactly. All right, so do we have everything we need for this integral?
Yes.
Okay. All right, well, then on your paper, solve this integral, okay? Solve this integral now. Anyone have an answer?
Yes.
All right. What do you got, Cade?
Z hat R to the 5th. Is that right? Over 5. Times 2 pi.
2 pi. All right. Anyone else? What do you think? This look good? Yes, no, maybe?
I also
About the same team.
got that, but I don't have the Z hat anymore.
Yes. Okay. So that's a good point, Mario, and you are correct. So what happens to this Z hat when we do the dot product?
Becomes 1.
It becomes 1.
Yep, it goes away. So when we have this vector dot with this vector, remember something dot with vector is this is going to be a scalar result. And because it's scalar, we will have this Z hat going away. So we shouldn't have the Z hat in our answer, but otherwise, yes, very nicely done. Okay. So now we have an expression, right, for the total amount of current, right, contained between 0 and some variable R. Okay, so we've just completed the region 1. So now let's look at region 2, and region 2 goes to A to B. So when R is larger than A, but still less than B. So completely containing this semiconductor, but not going all the way out. So completely containing this, but not going quite all the way out to B. So again, if we want to find all of that current, right, we can do the same integral. And does anyone already know what the result of this is going to be?
0.
So let's go back to here. Let's see. All right, so should probably change the limits, right? But this is going to be the same. We want to find all of the current contained within that whole region. So if we were to do that, what would the limit for R be? We want to find all of the current.
Well, into R.
So we go 0 to R, but once R gets as large as A, will there be any more current to add up? So we're trying to find the magnetic field in this region, and the magnetic field in region 2, right? This should come from all of the current that we can find that's less than B. So if we start here and keep getting larger, at some point, right, we leave the semiconductor and we leave the area that contains current. So if we want to find that total amount of current, the total magnitude of current, we only need to go up to A in this case. And phi will remain as 0 to 2 pi. All right, so any questions on this?
I can only see half the screen now. Oh, there we go.
Yeah. that better?
Yes.
Okay, does this make sense?
Yeah,
So similar to the Gauss's law, right? We'll need to include the current from each region we go out. We should take care to include the current from the previous regions. And in situations like this, where we go from a region that contains current to a region that does not contain current, we will need to check our limits and modify them a little bit from region to region so that we don't double add the current up, right? We should only end up adding that current one time each. So just like in the Gauss's law, we needed to be careful that we only added the charge one time each. All right, so take a moment and finish computing this integral. Shouldn't take too long. I think it's quite similar to the one that we just did. So let me know when you have an answer for this.
Pi a to the power 5.
All right. Pi a r 5. Is this what?
Pi a power 5.
Sorry, let's start over. So the first pi.
2 pi a to the power 5.
Okay, right.
5.
All right. Yes. Anyone else get that?
Yeah.
yeah, I
Yes.
got that.
Okay. Yes. So this is what I got also. Right. This should be all of the current contained in that region. So nicely done. Now let's go on to region 3, which is where the B, where the radius is less than or greater than B. So in here, but less than or equal to C up here. So we should again find that total amount of current contained in there. Okay, so the total current, right, contained, like if we're at this point here, for example, the total amount of current contained here, if we're at some R that's halfway in between B and C, the total current contained will be the current that we contained in here. So let's call this the magnitude I2 plus some amount that we've added up here. So if this is the magnitude I2, right, we've already found that current. And so we're going to need to come up with another expression now to describe the amount of current that's from here up to this point. So based on what we've done so far, see if you can set up this integral and solve it. Okay. So try setting up this whole integral and solving it. All right, so to do that, right, you'll need to select the J, which we should have some information about from the problem statement. You'll also need to select a DS, which we've just done. We did that in region 1. And then you'll need to choose some limits and complete the integral. Okay, so I'll give you a few minutes to do that. And once you have an answer, upload that to the Google Drive. Okay, anyone else get this? So for the J, right, we have minus z hat r cube. So minus z hat r cube, and then dot, right? So dot with r d phi dr, right? And that is the same as before. And the limits on phi go from 0 to 2 pi. And then the limits on r go from, let's see, what was it? From b to r. So they go from here, b, to some point r that's halfway across. So does everyone else agree with this so far? Okay. All right, and then the final result for all of that, for this integral. Did everyone else get this? 2 pi r to the 5th minus b to the 5th over 5.
Yeah, I got that as well.
Cool. And then this part, right, this is the total current from the magnitude of current I2, right? And this is the what we just added up, which gives us the total current contained anywhere from 0 all the way out to some r that's between b and c. So we have the I2 amount plus this amount that's in the region that's between b and c. All right, great. So the
You have
last,
to like add it all the time.
sorry, come again? What was
So
that?
I'm guessing that we were adding the current we had from A to that. Do we have to do that every time?
Yes, so from here on out, once you get, so when we start here, right, wherever we are, wherever you find, wherever you're at the radius, well, let me back up even further, right? We are trying to find an expression for the magnetic field at any point r, okay? And that point r could be within any of these regions, right? So if we want to find a magnetic field expression due to this structure, we could end up being anywhere in this radius, right? We could be inside of this semiconductor here, here, or outside. So to find the full and a full expression for R, what we should realize is that the magnetic field depends on how much current is inside of the radius of the point that we're looking at. So wherever we want to know the magnetic field at, if it's here, right, we know that the magnetic field there is going to include results from everything inside of that's contained inside of it, and so on as the further out we go. So as we continue going out, right, we need to include everything contained within the contour in order to get that expression for the magnetic field at this point. So when we're here, we include the total current contained there because the magnetic field relies on the current contained with that within the contour that you've selected. So when we're here, we need to include all of the magnetic field that's inside of it, or all of the current that's inside of it, and all the current that's inside of it comes from this region 1. So once we get out to this point, we're trying to find the magnetic field. We know that the magnetic field relies on the current, all of the current contained within the contour. So all of the current will include the current in this region 1 plus the current contained from B up to the radius that we're at. And so because of that, right, we need to include this amount, which this is the total current contained within the region 1, plus this new expression, which is the current that goes all the way out to some R that is in between B and C. Does that answer the question?
Yes, sir.
Okay, great. All right, so for the last part, right, for region D, region 4, what's going to change on this integral expression?
The limits for R.
Yeah, and what are the new limits going to be?
R equals C to R.
So we want to find all of the current. So now in region 4, we're somewhere right here. So we want to add up all of the current that's contained inside of here. Okay. So for here, right, our limits were from 0 to A. And if we want to include all of the current from here, we should go from B to what?
C.
Yeah. Well, if we integrate from B to C, we will get all of that current. So for part D, we'll go from B to C. Okay, so take a second and see if you can find that total current contained in region 4. So when you're at some radius that's outside, when you're at some radius that's outside of both of these semiconductor structures, what is the total amount of current contained within it? Should be pretty quick, right? So is this going to change? Is this I2 part going to change?
No.
Yes, that will be the same. What about in this? What will change?
Just R becomes C.
Yeah, exactly.
Pretty much it.
That is everything. So, all right, so now we have expressions for each one of the regions. Okay, so let's gather up everything that we know now. All right, so this was for region 1. Region 2. Region 4. Okay. So just like before, right, we wanted to come up with this expression for H phi. So in this case, right, H phi is equal to I over 2 pi r. So if we substitute this in, right, we have 2 pi r5 over 2 pi r. So some of this is going to cancel. And we get r to the 4th over 5. So this is h phi for region 1. And then for region 2, right, the 2 pi will cancel 2 pi. So we'll get a to the 5th over 5r is equal to h phi for region 2 with b. Does this make sense so far?
Yes.
Okay, so on your paper, what should h phi for this final one be? Take a minute and solve for that.
A to the 5 or 2r, 5r minus 5 minus 5.
All right, so I think oops, sounded pretty close. This is what I believe I got.
Yeah.
Okay. All right, so this is the result for D. I'll leave it to you to find C, but it's, you know, it's quite simple. It's very similar to the rest of these. All right, so this, right, this is, it took us a while, right? But this is how you can, we've returned to this Gauss's law type solution using symmetry. Instead, we're now looking at cylindrical structures with current, and we're finding the magnetic field, but it's very similar. You have a left-hand side and a right-hand side. Based on how we set it up, you solve the right-hand side once, and then you solve the left-hand side for each region. As you find the H field, the further out you go, you just keep track of how much current. So you start small and you keep going bigger, and you keep adding up the amount of current that is contained in larger and larger concentric rings that are contained in these different regions, until you arrive at expressions, right, where you have expressions for the current contained within each different region. And then you add them up as necessary, right? So this is the total current from the inner semiconductor, and you need to add it on here. Once you start getting into a region that contains the multiple semiconductor structures, you must add the current from the inner structure with the current from the outer structure. And then at the end, to get that full magnetic field, right, we've found the magnitude of the magnetic field in each case based on the current that we found. So hopefully that helps. On Thursday, you will take the quiz 5 first thing. We'll start class around 8:20. We will do a little bit more of this, and we'll look at magnetic boundary field conditions. If you have any questions, feel free to stick around, and if not, feel free to take off. So have a nice day.
Dr. Christ, I don't know if you do it on purpose, but I can't see assignments.
Okay, you can't see the assignments?
Yeah, I can't see homework 6.
Oh, okay. Shoot, yes. That, let me fix that. That is a good reminder. Let's see. Okay. All right, it should be available now. And yes, thank you. Thank you for letting me know.
I don't know if you still have the notes from the last time we practiced the exam questions.
Well, yes, I can send those to you also. Yeah, I was supposed to send those to you after we spoke, wasn't I? All right, hang on. See if I can pull these up. All right, I just sent them to you. Let me know when you have received them.